Greetings, geologists, and we're going to start the Jurassic period just because of the movies Jurassic Park and Jurassic World. This is the most famous name of the geologic timescale. We'll be talking more about that when we get to life forms of the Jurassic period, but I'll start with the introduction of the Jurassic by having you look at this dinosaur. Since we just talked about classification of dinosaurs, this is a Saurichian dinosaur, specifically a theropod. And it's not Tyrannosaurus rex, it's actually Allosaurus. So when you're looking at this guy and you're thinking about him, you can see the characteristics that makes him a Saurichian dinosaur. Now, he's going to be a late Jurassic dinosaur. Why was he not in the early Jurassic? Well, I think as we go through the climate, we look at the paleogeographic information, it'll become clear to you why certain animals could have lived at certain times during this geologic period. So it's important to discuss the stages of the breakup of Pangaea. If you recall from the Triassic, the first stage of the breakup occurred in the Triassic, and we're going to see stage 2 start in the Jurassic period, and stage 3, of course, throughout the last period of the Mesozoic and the Cretaceous. Couple of noteworthy things to point out that happened in stage 2. South America and Africa are going to rift apart, which opens the complete segment of the Atlantic Ocean basin. One way we know that is because of magnetic stripes that have been drilled through the deep sea drilling program and monitored, and data collected from those that show the oldest oceanic rock is adjacent to continents, for example, like North America, where we have very, very old oceanic floor, and it's really not that old, it's Jurassic in age. So essentially that means that the ocean floor has been recycled regularly when it comes in contact with the edges of cratons and has a subduction moment. Well, we've not had a subduction moment on the East Coast where that oldest material is since the late Paleozoic. So that's about the oldest stuff around, and that's pretty important to note. So the young stuff is going to be wherever we have major subduction zones. And I'll give you an example. The Nazca Plate would be a case in point where it's subducting against South America, and all the material is very young. We're talking like primarily Cenozoic in age. Some of it's like very, very recent. So the mid-oceanic ridges are continuing to spread and move those plates around, as we know from what you learned in physical geology. So as South America and Africa separate, I think it's noteworthy to point out that the ocean would have been not very deep at that time. So as sea level would go up and down with the full regression of the Arbsaroka and then the beginning transgression of the Zuni in the middle Jurassic, we would probably have stagnated water bodies, and we know we did because we have extensive evaporites. One area in particular we'll be looking at shortly. I think another noteworthy event for plates is to talk about what happened in Gondwanaland's case. Gondwana is going to begin to really break apart, and here's what's going to happen. Australia and Antarctica stayed joined at the hip for quite a while. They'll split up later on. Well, India begins to tear off. Remember, India is part of Gondwana, right? And it's certainly in the northern hemisphere now. So it's going to begin its journey across the Indian Basin starting in the Jurassic period. Another important thing to note is that Africa and South America kind of split away from the joint Australia and Antarctica. So that's going to begin to cause those continents to move in opposite directions. Well, as the continents separate, this is going to change oceanic currents. Oceanic currents dictate climate. Well, climate dramatically changes by the late Jurassic period, which is one of the reasons there's such a remarkable size of plant life and dinosaur life that occurs at the end of the Jurassic period. So when we're talking about the paleogeographic information of the Jurassic, a couple of things that I think you should kind of highlight for your notes, and that is the Arbsaroka finally regressed off of the craton. This is actually an important element for one of the rock layers we'll be discussing in a minute called the Navajo Sandstone. So we'll be coming back to that shortly. As the Zuni begins to start its transgression through the middle Jurassic, it will go all the way through the end of the Cretaceous to the early Paleogene. and then it fully regresses off of the craton. So it's at its peak by the late Cretaceous. So it's just beginning to flood the continent, but this Zuni transgression plays a huge role in what's going to happen with separating the North American craton into basically two halves. The eastern and western craton is separated by an interior water body. In the case of the Jurassic period, that's called the Sundance Sea. So the Cretaceous water body is called the interior Cretaceous Seaway. So just to clarify, the Sundance is Jurassic, and the interior Cretaceous Seaway is the Cretaceous water body. They are different sizes, but approximately the same location. I think it's important to point out here that if there's an ocean that floods from the north and the south into the middle of the craton there, you're probably not going to have a huge volume of terrestrial fossils in those areas except for the time frames that they were dry. However, the edges of those cratons would be like shoreline property, would be excellent real estate and habitat for terrestrial animals. So would the swamp areas, so would the terrestrial lowlands and the areas where streams and rivers would have been. So you have to kind of envision where we find Jurassic fossils matches where those areas are with what we know of the marine setting and the marine fossils we have from this time period. Another thing to point out is that we're going to have two mountain building events that begin but do not end during the Jurassic period. And we'll start with that one in just a second. So let's talk about the DeBadan Orogeny. I love this one, and here's why. One of my favorite national parks is Yosemite National Park. When I think about Yosemite, it just makes me smile because the granitic batholiths that make up this area are part of the Sierra Nevada range. And so when you think of the Sierra Nevadas, the big glorious mountains that extend all the way from along the western margin of our continent, you need to be thinking about Jurassic DeBadan Orogeny. Now keep in mind it does go through the part of the Cretaceous, so it's first uplifted in the Jurassic period, specifically the late Jurassic period. And it's going to create these massive granite plutons, and it's related to a plate that is subducting. If you recall from the Sonoma orogeny in the Triassic, it's the Farallon plate. So these granitic batholiths are still in existence today, and they're up and along our Cordillera belt, and they are famous, like Idaho batholith, the Sierra Nevada. I can just name a lot of them that are available to see. So when you look at the DeBadan Orogeny, you're going to see that these mountains would be along some areas right in here. And the mountains started to erode and sediments got deposited on the basins, which would have been these areas right here, which would have been the lowlands from the actual mountains at the base of them. So that's going to actually cause the Sundance Sea to start kind of retreating northward. And as that happens, we should see more terrestrial fossils in the area as the Sundance begins to move up this direction right here. And one of the famous rock layers that was deposited at this time is the Morrison Formation. Since the DeBadan Orogeny is late Jurassic, let me tie that with the Morrison Formation to make sure you're clear that the Morrison is a late Jurassic formation. We'll be looking at that in just a minute. Yosemite geologic story just begins with the DeBadan Orogeny, with the formation of the granite batholiths. Most of what we think of for Yosemite are the dramatic valley landscapes. Well, those are going to get made in the last ice age in the Pleistocene. So there's a story, kind of like we talked in some of these other periods, that just one thing is not the story of when you go to a park like the Petrified Forest, or in this case Yosemite. You're looking at a chronological series of events that makes up that geologic story, not just one isolated key event. It'd be like taking a person and looking at fourth grade as opposed to their entire life, right? I mean, that's just 1 year out of their entire existence. So you kind of have to look at the cumulative story whenever you look at rock layers and places that you go to understand the overall history. All right, the next place is named after a location in Utah. It's called the Sevier Orogeny. And so this one is interesting, and it's still Farallon. Okay, so here's what's happening. We get a pretty fast mid-oceanic ridge development out in between the Farallon and the Pacific Plate, and it's pushing the Farallon into our continent at a high angle of subduction. And that's important because it flattens out as we get into the fourth flux of mountain building that happens in the Cretaceous on into the Cenozoic. This area is going to impact essentially the same regions that we just saw with the DeBadan. So we're getting a series of problematic issues that are happening at the same time. So it's very complex geology. And this area is affected all the way from Mexico up through Alaska. So the severe orogeny is just another part of this story that affected the same region. And it's going to start in the late Jurassic and conclude in the late Cretaceous period. One of the things that I thought was interesting when I went on my sabbatical was finding evidence of this orogenic event. So the severe orogeny, since it had a high angle of subduction, a lot of the sedimentary rocks and even igneous rocks were metamorphosed in the area, and certainly this would be an example of an igneous rock that got metamorphosed. Ophiolites are very common when basalt or gabbro get metamorphosed, and that's exactly what you're looking at. This is the Josephine ophiolite, and you're looking at some of the clues that it's mafic or ultramafic, or the green crystals that you can see right in here. That's olivine. And so what has happened is those rocks got deformed and metamorphosed during this subduction event, and there's evidence left behind along that trail that shows that story. So that brings us in to the rock layers that we're going to learn about, and I sequentially put them in kind of chronological order for the Jurassic period, starting with the early Jurassic deposition of the Navajo Sandstone. So it may sound melodramatic, but the Navajo represents one of the greatest Aeolian events of all geologic time. And anyone who's had one of my classes will laugh when they hear that, because every class hears about the Navajo Sandstone. It's infamous, it's gorgeous, it's a remarkable, widespread geologic formation. So what is it? First of all, it's a cross-bedded, clean, quartz-based sandstone. Remember, what clean and mature means is well-sorted, right? In this case, it is high-angle dunes. So from what you've learned in this class, that means Aeolian, right? And that is different from beach, in other words, beach sediments only. In some literature you'll read, oh, the Navajo is just a right along the edge of the sea right here. Well, it could have been coastal dunes like you're seeing in this diagram, but this is a long way from the coast. So they're really called inland dunes. I'm certain we had coastal dunes, and you'll see parts of the Navajo that would have different types of cross-bedding. But what we're definitively seeing in the Navajo Sandstone are some remarkable sand dunes similar to what you would see in the Sahara Desert today. So this was impressive, and it's left behind this remarkable rock record that's in the Colorado Plateau. This is the Navajo Sandstone. Now, it exists outside of Zion National Park. You're looking at cross-bedded sandstones in Zion, but this is probably the best place to see them. Having said that, you can travel for 400 or more miles in all directions and see Navajo sandstone all throughout the Colorado Plateau. It's really incredible. So where did it come from? It was a major erg. What's an erg? It's a large sea of sand. So I always tell this to students, you don't just get sand magically. When we're talking about sand dunes, if you think back to physical, you have to have a source of sand. It doesn't just appear. It doesn't just fall out of the sky. That means something has to be eroded. So you have to think about what was present at that time. We have these new mountains from the severe orogeny, the DeBadan orogeny, the Sonoma orogeny, and what's left of the ancestral Rockies. So the ancestral Rockies and the erosion of these other mountains are going to play a huge role in the makeup of the formations that we see in the Colorado Plateau. That's certainly the case in the Navajo situation. There are major types of dunes found in the Navajo that are noteworthy to talk about. We see dunes that are the actual dunes themselves, and then the in-between land section that would be almost like where you have in scuba diving where you'll see a coral reef, you'll get sand in between those coral reefs. Those are channels, so we see the channels between them, which are the flat-lying areas. And within those sand dunes, we can see two major types of aeolian deposits. First of all are the wind-rippled layers, which are the pinstripes, kind of like what you're seeing right in here. And those would be on the windward side of the dune where the sand's being pushed up the slope. And then we see where the layers slump down the back side of the slope, and that's going to be the grain flow strata. So very noteworthy that you'll see some really remarkable stuff. While I'm here, I'll just point out this is a truncated dune right here where the top gets its top wiped off of the dunes, almost like an unconformable contact, but it just simply represents like a storm is what it represents, that kind of flattened out the top of that dune. And so we see that all throughout the Navajo, especially in the Zion area. Well, this is Zion again, and since I've got your eyes on this, note that the color is very different. So there's a reason for that. If you get tightly compacted sands, the iron that's in these sands doesn't have a good chance to drain when groundwater gets into it. But when the grains are bigger and there's a bigger space for permeable and porosity of sediments to move around and the water to move in between those sediments, then you're going to have a higher chance for what I would call leaching out of that iron, where it literally bleaches out the material and the iron gets washed out. So if you see a whitish sandstone and it's still the same unit as another section that's red, that's what you're seeing, is you're seeing grains that were tightly packed together that could hold the color, and then the ones that are more permeable and a higher porosity combined with that, allowing for water to be able to move through it, then you're going to see the effect of this right here. So this would have had a high porosity probably, but not the ability for permeability. This has both, but permeable for sure for the water to drain right through it, which helped get that white color. When you look at the Navajo and Zion, all of that's Navajo sandstone for the most part. There's a little different formation at the very top and a few at the bottom. This is a different formation down here. But all of this stuff that makes up these giant monoliths of sandstone, those are, no kidding, the same geologic formation, Navajo. So you're looking at several thousand feet of sand dunes. Now, I'm not in any way suggesting to you that at one time we had 2,000-foot tall sand dunes. What I'm suggesting to you is over a period of the early Jurassic, we saw this incredible aeolian event that produced large-scale sand dunes like the Sahara today. While you're in the Navajo, this is a common sight to behold where you see natural mass wasting, and rock slides are very common. This is a natural arch, so all that rock material that used to be there is down in the valley. And you can also see chemical weathering from oxidation. You can see the changes in the color within the sandstone itself. The sandstone's very porous for the Navajo, so it often produces groundwater seeps, and that's very common as you go through the parks. Now, this is not in Zion. This is in Page, Arizona. This is also Navajo. So this is called Antelope Canyon. It's a beautiful location. The reason it has this definitive canyon look, it's a slot canyon, is because of flash flooding, but it's still the same geologic formation. And my point for showing it to you is that it's a long distance away from Zion National Park, multiple hours a drive. So when you're looking at that, the sandstone was in multiple states. It wasn't just in one location. This is in Page, Arizona as well, at a famous place called Horseshoe Bend, and I'll show you what that looks like. But I took this picture on field course to kind of show the angle of the crossbeds, and we had our students doing an activity for strike and dip that day, and you can see how oxidized this part of the Navajo is compared to parts of the Zion area. This is Horseshoe Bend. Now, you're looking at a different type of feature where the river is, and if you've taken a physical course with here at MCC, you know that that's an oxbow in the make, but probably never will make because the Colorado has been tamed because of dams that have been put on to the river for water management control. So you have to imagine that this thing got carved out, the big horseshoe feature there. But what the point is from one side of the horseshoe to the other, from this side, the middle, and over here, it's all the same rock. And it's all Navajo sandstone, heavily cross-bedded stuff. Well, that brings us into another important early Jurassic deposit, which is the Luan salt domes. This is so important that we'll revisit it during the Cenozoic. Something I should tell you, a little forewarning about salt domes, is they're important to oil and gas. And here's why. They tend to be fairly buoyant in rock layers and tend to rise. It's almost like if you've seen a lava lamp, how the lava rises. Well, that's kind of what happens in rock layers with salt, and they can cause rocks to start fracturing, jointing, and faulting. And it's certainly the case with the Luan. But here's how the Luan salt domes got formed. Remember we talked about North America and South America splitting in the Triassic. Well, as they separated and continued their separation, the Gulf of Mexico began to have water, and it was just a small, minute bay compared to what it is today. So as the Arabsaraka Sea regressed, it left behind a lot of salt water in that area, and the deposits accumulated, and it created about 3,000 feet full of evaporite salt deposits, which made huge salt domes in the areas that I'm pointing to in the picture of the diagram of the United States and the Gulf of Mexico. So that's essentially the extent of the Gulf of Mexico, where you see the salt domes right there at that time. So the salt domes themselves, yay for salt domes, right? I mean, they're good for finding salt, but they're really important for fracturing rocks above them in geologic future. So the stories of those rocks that will be deposited haven't happened yet. So we'll wait to talk about them when we get to that point in the semester. When the Luan salt form, one of the important things to understand about petroleum stuff is to be able to interpret what happened. And I think this diagram is a really good illustration of that. These purple areas, first of all, you can see where it says Jurassic, and the S refers to the salt or the salt domes. And can you see how they've invaded these younger rock layers right here? Well, that's indicative of salt domes traveling and fracturing. These would be fault lines right in here. So that plays a very important role in the early Cenozoic rocks, where we get huge volumes of petroleum resources in the Gulf of Mexico. So this is a prelude to the importance of salt domes anywhere in the world, but certainly to our continent and the resources that we have for economic gain for petroleum. So associate the Luan salt domes from the early Jurassic with something important that will happen a little later on in geologic future, because these salt domes were deposited before the blue, the greens, the oranges, and the yellow layers were even conceptualized, before they were ever made. So as these rock layers compress against this, salt naturally starts to migrate up and starts to rise, and that's a very common look to how salt domes appear in geologic rock record. All right, the late Jurassic period, one of the most noteworthy formations in North America, is a very fossiliferous set of bones from the late Jurassic called the Morrison Formation. This is a unique member, or a unique formation. It has numerous members, and so when you're talking Morrison, you have to usually get a little bit more specific of which particular member you're talking about. Now, the Zuni transgression had already begun in the middle Jurassic and continued through the late Jurassic, and I think that's important to note because we find fossils of evidence of ancient life forms like plants that were in swamp areas and plants that were in river basins and forest, and we find evidence of dinosaurs, a very rich evidence, I might add. So they're deposited in a wide variety of depositional environments, and you look at this picture. This is out in the Hanksville area where the Mars Desert Research Station is. It looks just like the Chinle, doesn't it? Well, it may, but it is actually Morrison, and it has a lot of the same features that Chinle does, except it just happens to contain late Jurassic dinosaur fossils. So when you look at the Morrison Formation, it's overlain by an important rock that is the Dakota Sandstone, which is a group of rock layers, but the sandstone has actually kind of capped the Morrison in place. It acts as a cap rock, And I think that's important to point out because we may have had as rich of fossils elsewhere where we don't find Jurassic dinosaurs, minus where the Sundance Sea would be in North America. It's just that maybe those rock layers have been eroded away. There's an unconformable contact. It could be we've not discovered them yet either, but the Morrison Formation was kind of lucky. It got a nice hard rock put on top of it that has kind of held everything together. In the Morrison Formation, you will find a lot of very important dinosaurs: Camarasaurus, Diplodocus, Apatosaurus, Stegosaurus, Allosaurus, or just to name a few. And in certain quarries, which are dig sites, there have been numerous full skeletons of animals found. Ongoing research and discoveries have kind of redefined some of the lines of the existence of certain animals, and I think there's more to come on that in the future, but those works are in progress right now and not appropriate to discuss until they're published. This is the dig site at Burpee that's in Hanksville, and this is their dig site, and people are working on their fossils, extracting them out of the ground. So in the back you see the colored layers, very characteristic of the Morrison, and we're working in a sandy unit right here. Well, part of the unit's also very conglomeratic. There are very much lenses of conglomerates in the Morrison. So that kind of indicates that you've probably had flash flooding out in the area. I find it very fascinating when you look at the history of the rocks out there, and the Colorado Plateau where the Morrison Formation is predominantly found. It's found beyond that too, as an FYI. It's found in places like Montana. I mean, it's a very big geologic formation. So it's as different as the depositional environment would have been in a specific area, and the fossils will totally be directly correlated to the type of depositional environment in which they lived. When you look at the dig site, it's almost hard to imagine what this might have looked like in geologic past, meaning what kind of plants were there, the ecosystem. But much like the petrified forest, you have to take away the Badlands desert look here and replace it with the landscape that would have been in existence during the late Jurassic. Would have been enormous volumes of green stuff, plants everywhere, and those dinosaurs grew huge because of it. They had an enormous food supply, and that enabled them to get to these just incredible sizes of the sauropods that we see at the late Jurassic period. One place to really see excellent fossils of the Morrison Formation is Dinosaur National Monument. And I've had the pleasure and privilege of getting to see this location. It's very remote. It's not somewhere you're just going to go in a day. And you kind of have to be going there to get to the site. But it's a really remarkable remains of a quarry. And in that quarry, there are fossils that are in an in situ shelter. So in Waco, we have a similar in situ shelter over the Waco Mammoth site, which has recently turned into a national monument through the National Park System, Department of the Interior. So it's the same kind of setup where you have a building that's climate controlled over these bones, or what's left of the bones that are there. When you get there, it's just almost overwhelming. Everywhere you look, there's this really steep face, and when I mean steep, it's at a very steep angle, kind of like this, and you see all the bones that have been extracted that are in the ground. So the bones are literally in the ground, just like the Waco Mammoth site. And they're preserved where they're in location. Others have been taken away from the site. There was some poaching early on and some bones removed when the initial excavation occurred. But since the national park took it over, it's pretty much been protected in the ground as it is. When you look at the bones, it dictates a fauna of enormous dinosaurs, primarily large sauropods. There is evidence in fossils from predatory dinosaurs of the area, like Allosaurus, but most of the bones are from sauropods. And you look at the size of these bones, and it's humbling because you put together a story of enormous animals that were eating plants and stuff off of trees and ferns, and whatever they ate a bunch of it to get this large. So I just cannot imagine what it must have been like. And I think when we're getting to the point about life forms, I think this would be a good place to mention it, and I'll re-mention it in the life forms. If they ate that much, they're going to produce that much waste. So there's going to have to be something that's in the rock record, some kind of organism that can break down that amount of coprolitic material, and that would be dung beetles. So really, there should be a nice presence of attributes of ode to the dung beetles for doing their job, because they would have had an important job to do during the late Jurassic period. So that's a great place to take a break before we get into the life forms of the Jurassic, and I'm really looking forward to sharing that with you. So come back for the second half and you'll get to learn all about the important life forms that existed during the Jurassic period. See you back soon. Bye.